Okay, I would like to go over the Euler's Lagrangian equation. Starting with the definition of Lagrangian, it involves taking the difference between the kinetic energy and the potential energy. Now, the Euler's Lagrangian equation is a differential equation that solves for any force, position, or velocity solution. Its purpose is to solve with energies instead of being overwhelmed from using force vectors. Now, as you can examine closely, you can see that the equation has three independent variables. The time variable here on the farther left side, there's a position variable q on the farther right side, and in the middle there's the velocity variable q dot. Now the dot above q is representing as the differentiating q with respect to time, as you can see in this box. Now, as q dot represent the time variation of q, if we have q double dot, it should represent the second order time differentiation of q. Now, as q is the position, it means that this second order time differentiation should represent the acceleration, as acceleration is also the time derivative of velocity. Now, the Euler's Lagrangian equation is pretty much a force equation. And I'll write it right here. Now, redefining the Lagrangian, we have the Lagrangian equal to the kinetic energy minus the potential energy. Now, we understand that the kinetic energy is equal to half times mv squared. Now, as seen right here, since q dot also represents the velocity, we can make it to half times mq dot squared. Now, we can consider taking the partial derivative. Instead of the Lagrangian, we'll take the partial derivative of the kinetic energy. And I'll do it with respect to q dot. Now, following power rule, we will end up with this result. 2 over 2 times m instead of v, we'll have q dot. The 2 over 2 would just be 1, so we're left with m times q dot, which will be equal to m times velocity. And we include that will equal to momentum. Now, going back to the Euler's Lagrangian equation, we see that there is a differential operator with respect to time. So I'll write d over dt, and we'll have the partial derivative of the kinetic energy with respect to q dot. And we already defined the partial derivative of kinetic energy with respect to q dot to be the momentum. So it'll be d over dt, and then we'll derive the momentum with respect to time. Now, I will define momentum back to its velocity form. It'd be m times q dot. The mass is constant, so we will put it out and be left with q dot. Now, as mentioned above, we see that q double dot represents the second order time derivative of q. And that will equal to acceleration. And acceleration is the time derivative of velocity, meaning that it's the time derivative of q dot. So it'll be mass times q double dot, meaning mass times acceleration, which will equal to the force. Now, on the right-hand side of the equation, we will isolate just potential energy, as the left-hand side will have isolated the kinetic energy. Now, I'm not going to be much mathematical vigor, but we're just going to understand the definition of a conservative force. And as you can see where I've written, the conservative force will equal to the negative gradient of potential energy. And this is represented in all three dimensions, denoted by r to the third power. But I just want it in a single dimension and it's a little more familiar. Now I have in a single dimension where I just use I hat instead, and Q represents the position, and we have the negative partial derivative of the potential energy with respect to Q. Now I'll make it more relatable because I believe in spherical coordinates. I can put the partial derivative of the potential energy using the radius with respect to the radius in r hat. And I look for more familiar. And it's the same setup like this. So representing the Lagrangian, you have the partial derivative of the Lagrangian with respect to Q. And that's it. Now I'm going to go further in another video to derive the electrostatic force using the Euler Lagrangian equation. But that's all I have for right now. Thank you for who is watching.